Suppose that we're interested in comparing two different population proportions. So from one population, we can calculate the proportion or the success probability, and we want to compare that to a second independent population's proportion or success probability. In this case, as long as we're taking large enough samples from both of these populations and both populations are independent of one another, then we're going to be able to compare these and conduct statistical inference, whether that is confidence intervals or hypothesis testing, through the use of normal-based procedures, whether those are z-tests or normal-based confidence intervals. So statistical inference for population proportions can proceed by first using the normal approximation to the binomial and then applying the normal-based inferential procedures. So the normal-based approximation of the binomial, if we take x to be from a binomial distribution where the number of trials is nx and the success probability is px, then what x is doing is counting the number of successes if we perform nx trials where each has a probability of success of px, right? So we're always thinking about, for instance, the flipping of a coin. And we'd be flipping the coin nx times, and it would show up heads with probability px. In that case, x is going to count how many times did we actually see heads in those flips of the coin. We know from the binomial distribution that the expected value is always nx times px, and the variance is always nx times px times 1 minus px. So this is true of any binomial distribution. Now, if nx is large enough, and specifically large enough in comparison to px and 1 minus px, then x is going to be approximately normally distributed. And specifically, it's going to have an approximate normal distribution with a mean of nx times px and a variance of nx times px times 1 minus px. Right, so we have this normal approximate distribution here. Then the sampling proportion, right? So if we actually want to understand, well, in our sample, what is the proportion? We take the observations divided by the total number. So that's our sample proportion here. This is also going to have an approximately normal sampling distribution. And specifically, we can write that it's going to have an approximately normal with a mean of px, so the true proportion, and a variance of px, 1 minus px over nx. Okay, so that's going to be the normal sampling distribution for px. Now, if we assume that independently we also have y that's coming from a binomial with ny and py, then we can use the same argument to come to the fact that the sample proportion for y is going to be approximately normal with a mean of py, a variance of py, 1 minus py over ny. Right? So we have a normal sampling distribution for both sample proportions. So what if we ended up wanting to compare the proportions? We want to take a difference of these proportions. So if we want to compare px to py, then we're thinking about sort of px minus py as the quantity of interest. Using the sampling distribution results we had previously, what we can say is that, again, as long as our sample sizes are large enough that these approximations hold, then the difference in these proportions is also going to be approximately normal. It's going to have a mean of the difference of the population means, and then the variance is going to be the summation of the two variance terms, right? So px 1 minus px over nx plus py 1 minus py over ny. This is going to hold whenever x and y are independent of one another. Now, we need nx and ny to both be sufficiently large, right? But if that holds, then the sampling distribution here can be used. And it's going to be able to be used to form either confidence intervals or to perform hypothesis tests where we're thinking about these as all being normal-based hypothesis procedures. If we need critical values or p-values, we're going to be obtaining those through the normal distribution. So how do we go about forming our confidence intervals and hypothesis tests? Well, in this situation, we can turn to a standard z-based confidence interval. So we take our estimators for px minus py, plus or minus our z critical value at the alpha over 2 level, and then we plug in our estimated variances here, right? So it's going to be p hat x, 1 minus p hat x over the sample size, plus p hat y, 1 minus p hat y over the sample size as well. Okay. Now, z alpha over 2 is our standard normal critical value, right? So that's going to be for the alpha over 2 level. In the standard error expression, so when we're looking at our actual standard error over here, if you want to be conservative with our confidence interval, then what we can do is we can actually take both of these values to be 0.5, right? So we'd be plugging in 0.5 for p hat y, we'd plug in 0.5 for p hat x, and then in that way, we're going to be dealing with this as being conservative. Okay, and so we can always take that as an option. This is good if you want to be particularly cautious with your confidence interval. We can also change out the critical value that we have here to be, say, Z alpha or Z1 minus alpha in order to get a one-sided or perhaps an asymmetric confidence interval. So it's going to be a standard normal-based confidence interval once these approximations are known to hold. If instead we wanted to test the null hypothesis that the proportions were equal versus the alternative that they're not equal, what we can do is we can take our Z score. So we take p hat x minus p hat y, divide that by the standard deviation under the null hypothesis. So if p hat x and p hat y are equal to one another, then we can take a look at what this actually becomes up here, right? And if p hat x and p hat y are the same, then these two expressions are going to be equal to one another. And so then we get 2 times p, 1 minus p, right? This will be approximately normal under the null hypothesis. Here, our p hat that we're using in our standard error is going to be given by the total proportion. So we add up the success of x, the success of y, divided by nx plus ny. In terms of n, we are using this as the total number of samples, so nx plus ny. Okay. And so this is going to give us our overall Z score here. Now, importantly, when we're testing differences in proportions, we are only able to test if the difference in proportions is equal to 0. If you wanted to test is the difference in proportions equal to some other constant, we're going to have to use different methods for that. The normal approximation is really only going to hold if we can test them equal to 0, and that's because we need to be able to simplify down this variance term here, okay? And so the approximation is not going to work particularly well if you don't have them equaling 0, but there are going to be other techniques that just go beyond these normal approximation techniques. And so importantly, this null hypothesis is the only null hypothesis that we can test, except for perhaps making it one-tailed, right? So you could test greater than or equal to, that's fine, but it always has to be a 0 as the difference. The other thing to note is that if you want to make this a conservative test, then in our standard error, we can plug in 0.5, right? So we plug in 0.5 for p hat in those cases. We don't need to use the joint estimator over here, and then that's going to be a conservative test statistic. So let's take a look at some examples applying this then. In this first example, we're thinking about flipping a coin, right? And we have our 2 coins, we have our quarter, and we have our dime. We flip the quarter 50 times, comes up with heads 22 of those. We flip the dime 75 times, and it comes up with heads 40 of those times. And what we want to know here is, are these coins coming up heads with equal probability? Okay, and so we want a 95% confidence interval, and then we want to test this hypothesis with alpha equals 0.05. And so we can write down, well, what information do we actually have here? Okay, so we have n is going to be equal to 50, because we flipped it 50 times here. We observe x is equal to 22, and so then p hat x is going to be 22 over 50, which is 0.44. So we observe a 44% probability or proportion in our first sample. For our second sample, we take m is equal to 75. We take y equal 40. And so then p hat y is going to be 40 over 75, which is something like 0.53, I think. Okay. And so in that case, we are going to have our 2 different proportions here. And then what we can say is that under the null hypothesis, we're going to be dealing with our normal 0, 1, right? Or in terms of our sampling distribution, we'll be dealing with the normal 0, 1. So then we're going to want z of alpha over 2, which is going to be z of 0.025, since we have alpha equals 1 minus 0.95, which is our 0.05. Okay, so we have a 5% level of significance here. And so our normal distribution is going to work out here. Okay, so we can take all of this sort of together and start to walk through what is it that we can actually say in this setting. So pulling out this information, we have x22 and x50, so the proportion is 0.44, y is 40 and is 75, and so then proportion is 0.533. The sampling distribution is going to be approximately normal according to the actual true differences and then the true variances here. Okay. We want alpha is equal to 1 minus 0.95 or 0.05, and so then our critical value is going to be negative 1.96. We can get our critical values using the Q norm function in R. So we want the 0.025 critical value. You take Q norm of 0.025, that spits out negative 1.96. Okay, so then working on our confidence interval first here, what we can do is we can plug into our confidence interval formula, right? So we take our estimated differences here, plus or minus the critical value, times by the estimated standard error that we have. So plugging in, we have 22 over 50, 40 over 75, 1.96 is our critical value, and then plug in our proportion. So 1 minus 0.44 times by 0.44 over 50, 0.553 or 533 minus, or times 1 minus 0.533 over 75. Okay, and that gives us our interval here of negative 0.271 to 0.084. So that's going to be our 95% confidence interval for the differences in these proportions here. For part B, are they equally likely to show up? So in this case, right, we are now wanting to test, well, is the proportion actually the same? So we'll test the null hypothesis that px minus py is equal to 0 versus the alternative that px minus py is not equal to 0, right? All of the same information otherwise. We're still testing at alpha equals 0.05, and so that's where we're at, right? So test this null hypothesis. We get the common proportion here as the number of successes for x, which we saw was 22, plus the number of successes for y, which we saw was 40, divided by the total number, so that's 50 plus 75, right? 50 plus 75 here. So that means that overall, we had 41.6% heads show up. Okay, so we get that. And then we can use our common test statistic here, right? So the differences in our observed proportions divide by 2 times this 0.416 times 1 minus 0.416 over our total number, which again is this 50 plus 75 here. Okay, and so then by plugging in everything into the relevant spots, then we are going to get that the test statistic value is negative 1.497. And so if we want to get a p-value out of this, our value is going to be coming from our normal distribution. And so the p-value is going to be 2 times by the normal distribution evaluated at the value that we want, which in this case is negative 1.497. Okay, and so that's going to be our p-value here. We can get this out of statistical software using R. So we take 2 times p-norm of negative 1.497, right? P-norm gives us our phi value, and so then 2 times our phi value at negative 1.497 gives us 0.1344. And so the p-value here is going to be greater than our level of significance, and as a result, we're going to fail to reject the null hypothesis. So are the coins equally likely? Since the p-value, which we had as 0.1344, is larger than the level of significance, which we have as 0.05, then we fail to reject the null hypothesis. There is insufficient evidence in the sample to conclude that the proportion of heads from the quarter, which we observed as 0.44, is significantly different from the proportion of heads observed from the dime, which we observed as 0.533. Right? Those aren't actually significantly different in our sample at a 5% level of significance. Now, we could have used the confidence interval that we calculated directly to test this hypothesis, right? We could have actually said, well, is 0 in the confidence interval for the differences. And if you go back to look at the confidence interval we computed, you would find that 0 is in that. And so then we know at the same level of significance, we are going to fail to reject the null hypothesis. Okay. We could have also been more conservative in our assessment here. And in order to do so, we would have wanted to replace all of our standard errors with 0.5, or with the proportions in our standard error calculations should have been replaced by 0.5, right? So that would have made this a more conservative confidence interval or a more conservative hypothesis test. So in order to sort of understand that, let's take a look at a second example here, perhaps a slightly more real-life example, but let's try to approach these things conservatively. So a company is concerned that their hiring practices may suffer from unconscious bias. They decide to see whether their qualified male applicants are hired with a different frequency than their qualified non-male applicants. So they look at over the past year, the same position, the firm has hired 45 out of 100 from the pool of qualified male applicants and 18 out of 72 from the pool of qualified non-male applicants, right? And so what we've done here is we've specified that we're looking at the same position from the same firm, over the same period of time, right? Everyone in the sample meets the qualifications, and then we're just seeing at what rate were those individuals actually hired by the firm. We find that the males were hired with 45 out of 100 proportion, the non-males 18 out of 72. And so in this case, we want to form a conservative 99% confidence interval for the differences in these proportions, and then we want to test the hypothesis that the hiring frequency differs conservatively. So we want to test this conservatively with alpha equals 0.05. Okay. So once again, we can try to pull out any of the information that we have in this question. So in the first case, we're thinking about n is equal to 100, right? We have an observation of 45, and so then p hat of x is going to be 0.45. For the second population, we have an m of 72, we have a y of 18, and so then p hat y is going to be 18 out of 72, which is 0.25. Now, in our first case, we want to make a confidence interval, right? So we're going to be dealing with our z alpha over 2. Here, if we want to get alpha, that's 1 minus 0.99, right? So that's going to be 0.01. And the important thing when we think about doing the confidence interval or the hypothesis test here is because we want them to be conservative, if we think about, well, what is going to be the standard error, then in the standard error, we want to replace p hat x, p hat y, and p hat with 0.5. Okay, so then we can replace those values all with 0.5, and that's going to make these intervals wider. It's going to make the tests more conservative. Okay. So we can actually start plugging in these values and working out, well, what are the results that we get here? So we observe the information, x is 45 and x is 100. So the sample proportion is 0.45, y is 18 and y is 72. So the sample proportion is 0.25. We form the confidence interval with the alpha value of 0.01. And so Z alpha is going to be negative 2.58, right? If we want to get that using statistical software, we take Q norm of 0.005, right? So the Q norm of 0.005 gives us the negative 2.58 that we need here. In order to make these intervals as conservative as possible, then we will use 0.5 for our proportions in our standard errors. So to form this confidence interval here, we can look at the calculation, take our differences in our proportions plus or minus our critical value times by the estimated standard error. But when we actually compute our estimated standard error, instead of plugging in p hat and x and p hat y, we plug in 0.5 for everything, right? That makes it as conservative as possible. We plug in the other values that we have, and we get this interval from 0.001 to 0.3999. Okay? And so that's going to be our 99% confidence interval for the differences in these proportions. For part B, looking at the hypothesis test, we are thinking about testing the null hypothesis that there is no difference, right? So H naught is going to be that p hat or px minus py is 0 versus the alternative that px minus py is not equal to 0. And when we think about getting our test statistic out of this, right, we're going to be thinking about replacing the estimated value only in the standard error, right, with a 0.5. So that's going to be 2 times 0.5, 1 minus 0.5 over n. Okay, and so that is a 0.5 there. Okay, and so then by replacing these values and then plugging in the other values that we've observed, we can test the hypothesis in a conservative manner. Okay, so we take the null and the alternative equal to 0 versus not equal to 0. We plug into get our z-score here, right? And so plugging in 0.45, 0.25, and then we have 0.5 plugged in as our conservative value. We find that that is going to be a value of 3.709. Okay, so if we want the p-value, then under the null hypothesis, this is standard normal. And so the p-value is going to be 2 times phi of the negative version of what we're looking at here, right? We still are dealing with a two-tail hypothesis test, so it's 2 times negative 3.709. If we want to get this value, we can use statistical software. We take R, and it's going to be 2 times p norm, right? P norm giving us our phi, negative 3.709 is the value we have there. And if you actually plug that in, you get a value of 0.0002. Okay, and so this value of 0.0002 is going to be less than our level of significance here, and so we are able to reject the null hypothesis. So since the p-value, which we have as 0.0002, is smaller than the level of significance, 0.05, we reject the null hypothesis. There is sufficient evidence in the sample to conclude that the proportion of qualified males, which we observed to be 0.45, is significantly different from the proportion of qualified non-males that are hired, which is observed at 0.025, or 0.25 rather. Okay, and so whenever we are looking to test from two different populations, proportions, we want to compare these proportions, whether that's through confidence intervals or that's through hypothesis tests, then what we can do is we can apply the normal approximation. This is going to apply whenever our sample sizes are large enough, and we can use this approximation to form Z-based confidence intervals or to perform Z-tests. When we're performing those Z-tests, we have to be cautious that the only null hypothesis that we can test is when we are testing the difference being 0. If we want to test for non-zero differences, we're going to have to look for methods that are outside of using this normal approximation here. The other thing to keep note of is that if ever you want to make the results of your inference more conservative, you can take those values inside of your standard errors to be 0.5. That's going to be as conservative as you can be, and then you can trust those results that even if your estimated values are kind of far from the truth, you are ensuring that you capture sort of all of the uncertainty that might be there. And so then in doing this, you're going to be able to make statements either through confidence intervals or hypothesis tests about how independent binomial populations behave.